Welcome to Session 9. Today's equations come with fine print. When a system contains a square root or a variable in a denominator, there are values of x that are simply not allowed to exist. And here's what makes this session different from every other one. The algebra itself will hand you answers that are wrong. Not because you made a mistake. You can do every step perfectly and still produce a false solution. So today we learn where those phantom answers come from and the one habit that eliminates them. This is the session where checking your answer stops being optional and becomes part of the math. Let's understand exactly why squaring betrays you, because once you see it, you'll never forget to check. Squaring is not a reversible operation. It destroys information. Specifically, it destroys the sign. Think about it. 2 and -2 are different numbers, but square them and they're both 4. So when you square both sides of an equation, you're no longer solving your original equation. You're solving your equation or its negative twin, both at once. Take root of x plus 2 equals x. When you square both sides, the equation you actually solve contains the solutions of root x plus 2 equals x, and also the solutions of root x plus 2 equals negative x. Those extra solutions are real answers to a question you never asked. We call them extraneous. They're not errors. Let's watch it happen. Solve root of x plus 2 equals x. First, before any algebra, record the domain. Inside the radical, x plus 2 must be greater than or equal to 0, so x is at least -2. But there's a second restriction that students miss. The left side is a square root, so its output is never negative. The right side is x, so x itself must be greater than or equal to 0. Now square both sides. X plus 2 equals x squared. Rearrange. X squared minus x minus 2 equals 0, which factors as x minus 2 times x plus 1. So the candidates are x equals 2 and x equals -1. Check them in the original. For x equals 2, root of 4 is 2, and the right side is 2. True. Keep it. For x equals -1, root of 1 is 1, but the right side is -1. Is 1 equal to -1? No. So -1 is extraneous. And notice, our domain line already told us so, because we required x at least 0. The answer is x equals 2, alone. Let me prove that -1 wasn't random. It was the twins' answer. Our original equation was root of x plus 2 equals x. The negative twin is root of x plus 2 equals -x. Test x equals -1 in that twin. The left side is root of 1, which is 1. The right side is -1, which is +1. 1 equals 1. It's true, so -1 is a perfectly valid solution of the twin equation. Squaring merged the two equations together, and -1 came along for the ride. That's the whole mechanism. Extraneous solutions aren't mysterious, and they aren't your fault. They're evidence that squaring blurred two different questions into one. Now, denominators, which fail in a completely different way. A square root has values it can't accept. A denominator has a value that makes the whole expression undefined. If you see 6 over x minus 1, then x cannot be 1, ever, not for any reason. At x equals 1, you'd be dividing by 0, and that expression simply doesn't exist there. So the very first thing you write, before touching the algebra, is x not equal to 1. Here's why this matters so much. Your first algebraic move will be to multiply both sides by x minus 1 to clear the fraction. And the moment you do that, the denominator vanishes from the page. The restriction becomes invisible. The polynomial you're left with is perfectly happy at x equals 1. It has no memory that x equals 1 was ever forbidden. That's why you record the restriction first, because after clearing, the evidence is gone. Let's do one. 6 over x minus 1 equals x plus 1. Step 1 always, record the restriction. X is not equal to 1. Now multiply both sides by x minus 1. 6 equals the quantity x plus 1 times x minus 1. The right side is a difference of squares. Remember session 4. So that is x squared minus 1. So 6 equals x squared minus 1, which gives x squared equals 7, and x equals plus or minus root 7. Now check against the restriction. Is root 7 equal to 1? No, it's about 2.65. Is negative root 7 equal to 1? No. Neither candidate is forbidden, so both survive. Both are genuine solutions. Notice the difference from the radical case. There, one candidate died. Here, both live. The restriction is a filter, not a guillotine. Sometimes it catches nothing, but you still have to run it. So, here's your reliable 4-step process for anything with a radical or a denominator. 1. Record every restriction before you do any algebra. For a radical, the inside must be non-negative. And if the radical equals an expression, that expression must be non-negative too. For a fraction, the denominator can't be 0. 2. Transform. Square both sides or clear the denominators. 3. Solve the resulting polynomial as you normally would. 4. And this step is not optional. Substitute every candidate back into the original equation. Not the squared version. Not the cleared version. The original with the radical or the fraction still in it. Verification isn't double-checking your arithmetic here. It's the step that decides which answers are real. Let's do one from your practice set. Solve root of x plus 2 equals x, given the radical is real. Restrictions first. Inside, x is at least negative 2. And since a square root's output can't be negative, x itself must be at least 0. Square, x plus 2 equals x squared. So x squared minus x minus 2 equals 0. Factor, x minus 2 times x plus 1. Candidates, 2 and negative 1. Now filter. Negative 1 fails our x at least 0 restriction, so it's out. Verify 2 in the original. Root of 2 plus 2 is root 4, which is 2, and the right side is 2. It checks. The answer is A, x equals 2. And notice choice B is negative 1, the extraneous root, sitting right there in the answer choices, waiting for anyone who squared, factored, and stopped. Let's recap. Squaring is not reversible. It merges your equation with its negative twin, which is where extraneous roots come from. Clearing a denominator erases the restriction from the page, which is why you record it first. The process: restrict, transform, solve, verify. For radicals, check both the inside and the output sign. For fractions, exclude the zeros of the denominator. Test every candidate in the original equation, never the transformed one. And remember, sometimes every candidate survives, like our root 7 pair. The point isn't to throw one away. The point is to find out which ones are real. Well done on session 9. You now know why extraneous solutions exist, which means you'll never be surprised by one again. In session 10, we go visual, reading intersections off graphs, thinking in terms of the difference function, and learning when a picture can lie to you.